In the last section, you learned how to determine a confidence interval for a population mean mu when the population standard deviation sigma is known. But what about when it's unknown? So in the last examples, we use the standardized version of X bar, and this is the Z interval procedure, or the Z1 mean hypothesis procedure, which is equal to X bar minus mu over the square root, over sigma divided by the square root of n. And so this is from our table 2. But again, we don't always have all the pieces of information we need. We don't have the population standard deviation. In this case, we can't base our confidence interval procedure on the standardized version of X bar. The best that we can do is estimate our population standard deviation sigma by the sample standard deviation S. So in other words, we're going to replace our sigma with S. And in this way, we can now use the t distribution. And I put a video, I think it's in the next module, about this distribution. Is very interesting. In 1908, William Gossett determined this distribution that we call our studentized t distribution, or the studentized version of X bar. And this is the equation for it, or your key fact, the studentized version of the sample mean. Suppose the variable x of a population is normally distributed with a mean mu. Then for samples of size n, the variable t equals x bar minus mu over the standard deviation divided by the square root of n, and has the t distribution with an n minus 1 degrees of freedom. So let's talk about the t distribution and talk about some of the properties that go along with it. Now, there is a different t distribution for each sample size, and we identify a particular t distribution by the numbers of degrees of freedom, or you'll see it as df. And for the studentized version of X bar, the number of degrees of freedom is one less than the sample size. So symbolically, we'll say df is equal to n minus 1. Now, without getting too deep into what df really is, you can think of it as a currency you need to pay in order to run a test. And it will become more important later on as well when we get into 2 samples. So we've got different t curves, and they're all based on their df. So you can see that we've got this t curve here, which is the blue line, and it only has degrees of freedom of 1, which means that the sample size was only 2. So it will be n minus 1, so 2 minus 1 is equal to 1. But as the sample size increases, you can see from this orange line here, with a df of 6, it's starting to look more and more like the standard normal curve. And so a variable with a t distribution has an associated curve called the t curve. And there is a different t curve for each number of degrees of freedom, and all t curves are similar, and they'll start to resemble the normal standard curve, especially as the sample size increases. Let's look at the basic properties of our t curve, and this is kind of similar to when we were learning about table 2, so you can imagine that there is a t table that you're going to have to use in the future. So the basic properties of the t curve. Property 1, the total area under a t curve equals 1. A t-curve extends indefinitely in both directions, approaching but never touching the horizontal axes as it does so. So this is an asymptote. A t-curve is symmetric about 0. And as the number of degrees of freedom becomes larger, t-curves look increasingly like the standard normal curve. And of course, we're going to talk about how you can use the t-table. So percentages, and of course probabilities, for a variable having a t distribution equal areas under the variable's associated t-curve. And so for our purposes, one of which will be obtaining confidence intervals for a population mean, we don't need a complete t-table for each curve. We only need certain areas that will be important to us. this is the anatomy of the t-table. So if you go into your notes package, you will find a t-table, and it looks just like this one here. And so the two outside columns of the table are labeled DF. So you can see DF on this side and DF on that side, and they display the number of degrees of freedom. And as expected, this symbol denotes the t value having an area alpha to its right, so you can see that here, under a T curve. And so the column head up in here, for example, contains your T values that have areas, say, for example, 0.10 to their right, or T values having 0.05 to the right. So it'll be important now for you to grab out that t-table so that you can practice along with it so you understand exactly how it works. So let's do an example, finding the t value having a specified area to its right. For a t curve with 13 degrees of freedom, determine t 0.05. That is, find the t value having area 0.05 to its right, as shown down in the figures. So if you pull up your t-table, what you're going to do is you're going to go down the column on the degrees of freedom to find 13. Once you find 13, you're going to go across the top and you're going to get to T 0.05, and you're simply going to just intersect those two together and match them up, and you'll find 1.771. And I have a copy of that t-table here. So of course, we're going to go down the DF. We find 13. We'll go across the top to T 0.05, and we match those up together, and we get 1.771. So just a few notes about the table. It generally will contain degrees of freedom from 1 to about 75, but then they'll only just jump up to selected degrees of freedom. And it's really generally because they're for smaller sample sizes. If you've got a really large sample size, then you would probably use the Z tests. If the number of degrees of freedom that you're looking for isn't on your table, you can use like technology or go online to find a more detailed table. So also, as noted before, t-curves will look increasingly like that standard normal curve as the number of degrees of freedom gets larger. So when you get higher than, say, 2000 on your DF, then they're basically the same thing. So that's why it gets stopped early. Now, the values of given at the bottom of the table are accurate to about 3 decimal places. And so sometimes you might find that it differs from other sources that you use. The other thing that I want to mention about the t-table is that they are symmetrical to each other. So if you're looking for something in the t-table and it's 1.771, then on the opposite side of it, it will just be negative 1.771. Okay, so we've talked a little bit about these t-distributions and t-curves, and now we can develop a procedure for getting a confidence interval for a population mean, but this is when our population standard deviation is unknown. And we're going to proceed in essentially the same way we did for when the population standard deviation is known, except for now we're going to use our t-distribution. And so we'll go through the procedure for this. All right, this is the procedure for the one mean t interval, and the purpose is to find a confidence interval for a population mean mu, but the checklist of items that we need has changed a little bit. So it is our assumptions or our checklist will say it's a simple random sample, it's a normal population or a large sample, so again, QQ plot or a Shapiro-Wilk, and that their standard deviation is unknown. And then for confidence level of 1 minus alpha, we use the t-table now to find t alpha divided by 2 with df n equals minus, or df equals n minus 1. And so this is the formula. It's all pretty much the same except for that t alpha divided by 2, and then we're going to use a sample standard deviation in here, and so we can use that to approximate. So we really need to put this into play, which we'll do next. All right, let's do an example here. And so typically on an assessment, you wouldn't be given all of the information. You would get a chart with data in it, and using that chart, you would be able to calculate your N, your X bar, and your standard deviation. So if you had a hard time calculating sample standard deviation in the beginning of the course, make sure that you go back and refresh yourself with that. Make sure you're solid on how to do it because you need it going forward. So using the information given, find the 95% confidence interval for the mean loss mu of all overcharging offenses on pharmaceuticals. So we've got N, we've got X bar, standard deviation, and a 95% confidence level. So remember, 1 minus alpha, or 0.95, is equal to 0.05 divided by 2, as stated in our equation for T alpha divided by 2. And we get 0.025 and a DF of 25 minus 1, which is 24. Now, I encourage you to pull out your T table right now, and using 0.025 and 24 for your DF, try to find your T alpha divided by 2. Pause the video, try it out, see if you can get it. And the rest of it, you're just putting it into the pieces of the equation. So X bar plus or minus your T alpha divided by 2, which should be 2.064, multiplied by your standard deviation over the square root of 25. And then we do it again so that we can do it on the addition side. And so we can be 95% confident that the mean loss of all of the overcharging offenses for pharmaceuticals is somewhere between $405.07 and $621.57. So it's important that you calculate that right now and see if you get that same answer. And that brings us back around to a question you might have. What if the assumptions or the checklists are not satisfied? Well, again, you can use a non-parametric method that don't require an approximate normality, or you can increase your sample size, or N, to satisfy the assumptions. And at the very, very end, you can also transform your data to improve normality. So you can take all your data and you can log it, you can square root it, you can square it and see if your data will be transformed to being normal. So you've learned about the margin of error for the estimate of the population mean for Z alpha divided by 2 multiplied by sigma over the square root of n. So the margin of error in this case, when the population standard deviation is unknown, is actually equal to T alpha divided by 2 multiplied by S, or the sample standard deviation, over the square root of n. The margin of error in this case has the same basic properties regarding confidence level and sample size as the last time when we did know sigma. I want to bring your guys' attention to your formula card. And when I said notes package earlier, I did mean like the notes package showing your formula card and all of your tables in it. Now, when you look at your formula card, just know it is almost like a little cheat sheet for you. So you can see that they give you all of the information and the assumptions that you need to run the test. So for example, if you look at the Z interval for mu, we've got our standard deviation is known. It's a normal population or a large sample size. But then as you move along and you start to get over to the T interval, you'll see that we do not know the standard deviation. And these are the assumptions. So don't sleep on the fact that your formula card is like kind of a cheat sheet.